So today we're looking at 8.7, okay, to start off with, which is on finding rational roots. So as a quick reminder, let's talk about what a rational number is. A rational number is a number that can be represented as a ratio, hence the word rational with the word ratio in it, of two real integers. So 3/4 is the example I wrote down on the screen, or it could be 2/3, or it could be 1/3. What it can't be is pi, or square root of 2, or anything like that. Okay, so make sure we remember that a rational number has to be some sort of ratio or a fraction. So what this means for 8.7 is that the theorem we're going to be using a lot in this lesson is the rational root theorem, which, going through all that formal definition, essentially tells us that there's a way to find every possible rational root. And I say possible, not all of the rational roots, because we have to test to see if all of them work, or which ones work, I guess is really the way to think of it. But every possibility. So it gives us our options, then we pick the ones we think work best, and that end up working. So the formula is plus or minus the factors of the constant, or last term of the polynomial, so usually it's a number, okay, so like 2, divided by the positive and negative factors of the highest degree's coefficient. So if the highest degree is x to the fourth and its coefficient is 1, then the factors of that would be plus or minus 1, okay? So let's go ahead and look at an example of this. My example that I have written on the screen is 2x to the fourth plus 3x cubed minus 7x squared plus 3x minus 9. So my highest degree for my coefficient is 4, right there, okay? So my denominator of my formula is going to be factors of 2, and it's going to be the positive and negative factors of that. And then my constant, or my last term, my polynomial, is -9, or we really just want the number, not the sign, okay? So my numerator is going to be plus or minus the factors of 9. Okay, so the factors of 9 are 1, 3, and 9. So we get plus or minus 1, plus or minus 3, plus or minus 9. And the factors of 2 are 1 and 2, so plus or minus 1 and plus or minus 2. So now we have to compare each factor. So that means we're going to take 1/1, 3/1, 9/1, 1/2, 3/2, and 9/2. So our potential possible factors are plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1/2, plus or minus 3/2, and plus or minus 9/2. Okay? And in your notes, I reorganized that to go a little differently with the fractions first, but that's besides the point, okay? So the reason why 1, 3, and 9 are rational is because they can be represented as 1/1 or 3/1 or 9/1 respectively. So that's why they're rational numbers. And so that's my list of all possible rational factors. So now let's look at some examples from the classwork. In the classwork for this section, we're just doing the oral exercises, okay? So to begin with, let's look at number 4. For number 4, all I want you to do is list all possible factors, rational factors, okay? So list all possible rational factors. So we're going to do the formula we just did on the last slide. So my constant is 6, so I'm going to look at the factors of plus or minus of 6. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, divided by my factors of my highest degree's coefficient, which is 4. The degree is 4, so the constant is 1. So I'm looking at plus or minus 1. So my possible factors are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And that's it. Okay. Then let's look at 10. For 10 on the oral exercises, I want you to find all rational roots. So what's the difference between finding and listing is that listing, we just go as far as listing every potential possibility. For 10, I want you to find only the ones that work. So you're going to list all of the possibilities, and then we're just going to test to see which ones give us what we're looking for. So for 10, my possibles are the factors of 4, so that's plus or minus 1, plus or minus 2, and plus or minus 4, divided by the factors of 4. So plus or minus 1, plus or minus 2, and plus or minus 4. So my possibles are going to be plus or minus 1, plus or minus 2, plus and minus 4, plus and minus 1/2, plus and minus 1, plus and minus 2, plus and minus 1/4, plus and minus 1/2, and plus or minus 1. If you notice though, we have a couple of repeats. We see 1 3 times, so we're just going to copy that once. Okay, so 1, 1, and 1. So one of my possibles is going to be plus or minus 1. And then we see 2 twice, so 2 and 2. So we got plus or minus 2. And then we see 1/2 twice. So we're going to copy that down once. And we see 1/4 once, and then we see 4 once. So those are all my possibles once we've compiled all of them together. From here, we need to test to see which ones are going to synthetically divide our polynomial. So I'm going to set up my synthetic division first. 4, 4, 17, 6, and 4. And then I'm going to pick my factors. Now, let's start off with -1. So, -1. We bring down the 4. -1 times 4 is -4. 4 minus 4 is 0. -1 times 0 is 0. 17 plus 0 is 17. -1 times 17 is -17. 6 minus 17 is -11. -1 times -11 is +11. That's 15. In order for this to be a root, remainder has to be 0. We reviewed that yesterday, okay? So -1 is not a factor. So what's nice about the way that we set up our synthetic division bar is that I'm just going to cross out this work here, erase the work in between the two. If I had a smaller eraser, that would work. Okay. And then try again. So this time, let's try a fraction. Let's say we should try -1/2. So bring down the 4. -1/2 times 4 is -2. 4 minus 2 is 2. -1/2 times 2 is -1. 17 minus 1 is 16. -1/2 times 16 is -8. 16 minus 8 is 8. -1/2 times 8 is -4. 4 minus 4 is 0. This is 0. We're good here. So now we have one of our factors. So we're going to write out what our new polynomial is and use the factor theorem from yesterday's video to help us decide where to go from here. So we have x plus 1/2 times, we go down in 1 degree, so the highest degree was 4, so now it's cube, 4x cubed plus 2x squared plus 16x plus 8 equals 0. Okay? From here, there are 2 steps you can do. You can either factor, which is what I'm about to do, or you can synthetically divide again with the new polynomial, just like we did in last night's lesson. So I'm going to factor. So I have x plus 1/2 from here, okay? And then I have my new quotient. So I can factor out from the first 2, which I'm factoring by grouping. I can factor out a 2x squared. So I'm left with 2x plus 1. And from the second 2, I can factor out an 8. So plus 8, 2x plus 1. Now that I have something in common between 2 terms, I can factor out 2x plus 1. So I have x plus 1/2, 2x plus 1, and 2x squared plus 8 equals 0. I can factor out a 2 from my last factor back here. So 2x plus 1/2, 2x plus 1, x squared plus 4 equals 0. So now that I've factored it completely, I'm going to read off my factors. I've got x equals negative 1/2, negative 1/2, and then x squared plus 4 equals plus or minus 2i. The only problem with that is that plus or minus 2i is not a rational root. And I only want rational roots. So my answer is actually just x equals negative 1/2. And then I put a little double root next to it. But again, that's extra. Okay? All right. So now let's move on to 8-9. 8-9 is on linear interpolation. It sounds really complicated. It's actually not that bad when you get down to it, okay? What linear interpolation is that say you're given a set of data, like you would be on the SAT maybe, okay? And they say, find this random value for a year that isn't in the data set. How do you figure that out? Well, you use linear interpolation, okay? So for linear interpolation, the table we're going to use for 4 is going to be on 391, all right? It's with years and US population in millions. And what they want us to find is the value of the population in millions in the year 1976. Now, we aren't given 1976 in the table. In the table, we're given each decade. So we've got 1910, 1920, 1950, 1960, 1970, 1980, but not 1976. What's nice about linear interpolation is what you do is you find the two closest years, one that's larger, so higher up in the years, and one that's smaller. So one that's 1970 and one that's 1980. That sandwiches 1976 between them, which is nice, okay? And the difference between 1970 and 1980 is 10 years. We want to use that number because 10 is one of the easiest numbers to use when we're dividing numbers, okay? And then we want to figure out the difference between 1970 and 1976. That would be 6, okay? We're essentially, what we're doing is we're preparing to set up a proportion, okay? So I know you guys really liked proportions, so we're going back to those. So then, now that we have our years proportion set up, so 1970 1976 is related with 6 years, and 1970 1980 is separated by 10 years, okay? The population in millions, we don't know the difference between 203 and our potential population in 1976, so we're going to name that D, okay? And then we want to figure out the distance in millions, the difference between 227 and 203. That's 24. Make sure always your numbers are positive, so it should be the largest minus the smallest rather than the other way around, because in this chart, the data is increasing as the years increase, okay? So here, our proportion is going to be 6 over 10 is equal to D over 24. So the difference between the population increase in 6 years is equal to D, and the population increase in 10 years is equal to 24 million. From here, all we need to do is solve for D. So what I'm first going to do is reduce the fraction on the left to be 3/5, and then I'm going to multiply both sides by 24. So I get 72 over 5 is equal to D, and this is approximately 14. So we always want to round up to a whole number with these. We don't want to use decimals, okay? So we know that D, the difference in increase from 1970 to 1976 in population is 14 years. If that being the case, 14 million, sorry, we're going to then find P by adding 203 to 14. So 1970s population, 6 years increase, okay? So it's actually 217 million people were living in the US in 1976. Another nice facet of linear interpolation is that we can go the other direction and do what's called inverse interpolation, okay? Which means instead of being given our input, which would be years in this case, we're actually given the output, so that in some year, we don't know when, there's going to be 220 million people living in the US. And so what we want to do is figure out what year that's going to be. Now, the way to do this is similar to how we found our year choices, right? Because there is no 220 exactly on the data set, just like there's not exactly going to be the same thing on the SAT. So instead, we're going to pick the two numbers in millions for population that are nearest to 220. So just like before, we're going to pick one that's smaller than 220, in this case 203, and one that's larger. And it has to be the closest, okay? It cannot be like 220 and then you got 195. It has to be the closest possible. So now we need to figure out the difference between each. The difference between 203 and 220 is 17 million. And the difference between 203 and 227 is 224 again, okay? And then we need to figure out what the other side of our portion is, because right now we have 17 over 24. We need to figure out what the left side is going to be. So the difference between 1970 and Y, we don't know yet. So I'm going to name that C. And then the difference between 1970 and 1980 is 10 years. So over 10 years, population increased by 24 million. And over C years, population increased by 17 million. And just like with 4, we're going to multiply both sides by 10 and solve for C. So C is going to be equal to 170 over 24, which is approximately 7. So in 7 years, population is going to increase by 17 million. So what we need to do is figure out what year that's going to be. So we're going to take our original, which was 1970. It's our starting point, and we're going to add 7 years. So then that's going to be 1977 is when we have 220 million people living in the US. Now let's look at number 12. 12, we're going to switch it to a different chart now. We're going to use the chart on 392, okay, which is all to do with altitude and density. So our units are going to change to meters and kilograms per meters cubed. So in 12, they give us 320 meters, and they want to figure out what's the density going to be when we're at 320 meters. So just like with number 4, we're going to set it exactly the same. I found the two closest numbers to 320 meters. That would be 0 and 500, okay? And then we need to match the densities. So 0, at 0 meters, the density is 1.225, and at 500 meters, the density is 1.167. And what we want to find is the value in between those two. So what we're going to do is we're going to, again, find the difference. So between 0 and 320, that's 320 meters. That's how far up we went. And from 0 to 500, we went up 500 meters. Now, if you look at the chart on 392, you'll notice the density decreases as the altitude increases. So that means we're going to be using the top number and subtracting it from the bottom. So 1225 minus y, we're going to name that d. And 12.225 minus 1.167 is going to be 0.058. So that means our proportion is going to be that for 320 meters, our density changed d, kilograms per meter squared cubed. With a 500 meter increase, our density decreased 0.058 kilograms per meter cubed. So just like with 4 and 8, we're going to multiply both sides by 0.058 and solve for d. So what I end up with is that 0.928 is divided by 25. It is equal to d, okay? And that is approximately 0.03712. Okay? If you notice though, all of the decimals in the chart only go to 3 places. So our answer needs to be only to 3 places. So to find our actual answer for y is going to be 1.225 minus d, because we are decreasing in density. So that's going to be approximately 1.225 minus 0.03712, which will approximately be 1.188 kilograms per meter cubed. Now let's look at 16. 16 says 0.930 kilograms per meter cubed. So they gave us the density this time, so we're going to do inverse interpolation here. So for 16, we have to find the 2 closest densities that would sandwich 0.930. And that would be 0.957 and 0.909. So we need to figure out the differences between each. So 0.957 minus 0.930 is going to be equal to 0.028. And 0.957 minus 0.909 is going to be 0.048. And that should be a 7. 0.027. Okay. And then we need to figure out the differences between my altitude. But remember, altitude is increasing while density is decreasing. So we're going to actually subtract 3,000 by 2,500. So we get that the difference in altitude is 500 between 3,000 to 2,500. And the difference between x and 2,500 is just going to be d. So now let's set up our proportion. So d over 500 is going to be equal to 0.027 over 0.048. So when we increase by d meters in altitude, we decrease by 0.027. When we increase by 500 meters altitude, we decrease by 0.048 in density. All right, and now we just need to solve for d. So d is going to be equal to, that's an ugly d. D will be equal to 281.25, which, if you notice, all of our altitudes have no decimal places. So we're going to round to the nearest whole number, which is approximately 281. So to figure out how high in altitude we went after 2,500, we're going to add 2,500 to 281. That'll approximately be 2,781 meters. So at 2,781 meters, we have a density of 0.930 kilograms per meter cubed. Now let's move on to 18. In 18, we switch charts again. Okay, this time we're looking at the chart on pages 810 and 811 in your book. So that's all the way in the back of your books. And this time we're looking at square roots. So in 18, we're given the square root of 4.87, and we want to approximate what that value is going to be. And in the chart, they give us decimal places, okay, and they give us decimals, but they don't give us decimals to the 100th. They usually only give us decimals to the 10th. So we need to find the decimals that are closest to 4.87. In that case, it would be 4.8 and 4.9. And the value of the square root of 4.8 is 2.191, and the approximate value of square root of 4.9 is 2.214. And we want to find the value in between those two. So the difference between 4.8 and 4.87 is 0.07. And the difference between 4.8 and 4.9 is 0.1. Then the difference between 2.19 and y is the letter D, again, because we don't know what y is yet, and we're solving for that. And then the difference between 2.191 and 2.214 is 0.023. So we're going to set up our proportion. We've got 0.07 divided by 0.1 is going to be equal to D over 0.023. We want to solve for D. So D is going to be equal to 0.0161 because we multiply both sides by 0.023. And then we're not done though. We want to figure out what the approximate value of 4.87 is. So the approximate value of 4.87 is going to be equal to 2.191 plus our d, which is 0.0161. So that's approximately 2.207. Again, we round to the third decimal place because in the chart we go 3 decimal places. So that's our answer. Okay, now let's look at 20. In 20, it's different than 18 in that in 18 we were given 4.87, which was a ones digit followed by two decimal places. In 20, we now have a 10 and a ones digit followed by 1 decimal place. So what we need to do is figure out what 24.2 is equal to when we divide it by 10. And the reason why we divide it by 10 is because we want to move the decimal place over to the left ones, because our chart only has numbers with a single digit on the left side of the decimal. So 24.2 divided by 10 is going to be equal to 2.42, like so. So now that we have 2.442, we're going to rewrite our square root as the square root of 2.42 times 10, because that's what we did. What's nice about the charts that we have in 810 and 811 is that they include columns just for this type of situation. So we find our n, which in this case is between 2.4 and 2.5, and then we look at the column that says square root of 10n, because that's what we have, 10 times our number, and we read off our values. So 2.4 corresponds with 4.899, and 2.5 corresponds with 5.000. And then we're going to solve using proportions on this. So 2.4 to 2.42 is 0.02, and 2.4 to 2.5 is 0.1. 4.899 to y is d, and 4.899 to 5 is 0.101. From here, we're going to set up our proportions. So 0.02 over 0.1 is equal to d over 0.101. And then we're going to solve for d. So d is approximately 0.0202. So our approximation of our radical is going to be 4.899 plus 0.0202, which is going to be approximately 4.919. Now let's look at 22. In 22, instead of being given a square root, we're given a cube root. And instead of being given one digit followed by decimal, we're actually given an entire whole number. This time we're given 526. Now, what's nice again is that our charts do include a cube root section, and they also include when we multiply our number by 100. So we need to get 526 to look like 5.2. In order to do that, we need to move the decimal over 2 places. So we're going to divide 526 by 100. That's going to move our decimal over 2 places, so we get 5.26. So what we're really doing is finding the cube root of 5.26 times 100. Okay, so now that I have my digit all fixed, I'm going to look for the 2 closest numbers, which happen to be 5.2 and 5.3. And then because I'm doing 100 times n under a cube root, I go to that column. So 5.2 corresponds with 8.041, and 5.3 corresponds with 8.093. Knowing that, I'm going to start by setting up my variables and proportions. So the difference between 5.2 and 5.26 is 0.06. The difference between 5.2 and 5.3 is 0.1. The difference between 8.041 and y is going to be d. And the difference between 8.041 and 8.093 is going to be 0.052. From here, my proportion is going to be 0.06 over 0.1 is equal to d over 0.052. And now I'm going to solve for d. d will approximately be 0.0312. So my approximation of my cube root of 526 is going to be 8.041 plus 0.0312, or 8.072. Okay, and that's it. This is the last video that belongs to this section before the test, okay? So your test is going to be next week on Thursday and Friday. All right. And the classwork for Tuesday and Wednesday will be 384, oral exercises only, numbers 1 through 11 odd. Instructions are in the parentheses. And page 394, numbers 1 through 23 odd.